Welcome back to another video. Today we will study number theory in chapter 2, divisibility. And then we are going to the first topic of divisibility, which is the division algorithm. So let's get started. So when we divide an integer by integer, we can use a long division. For example, when you want to divide the number 112 by 20, what do we have? So try to use a long division. So we're going to have 20 divide 112. So what is the closest? What is the closest one that multiply 20? So that is close to 100. Is 5. Okay? Because 5 times 20 is 100. And then we subtract this number by 100, so it turns out to be 12. Okay? Once we have the result of the subtraction less than the divisor, we end the process of division. So we're going to have this result. So these numbers, this number is the quotient. Okay? This number is the remainder. And 20 is divisor. Divisor. Okay? And this number is dividend. Okay? Dividend. So, what do we have right here? We're going to have that dividend equal divisor times quotient plus remainder. Okay? So, this means that This means that any integer can be written as this form: divisor times quotient plus remainder. Okay? So, in conclusion, the quotient of 112 when it is divided by 20 is 5. The remainder of 112 when it is divided by 20 is 12. Okay? So this is division algorithm, which is dividend equal divisor times quotient plus remainder. So let's take a look at the formal theorem of the division algorithm. So we let a and b be integers such that a is not 0. Then there exists a unique pair of integers q and r such that b equal to a times q plus r, where r is greater than or equal to 0 and less than absolute value of a. And q right here is called the quotient. R right here is called the remainder. What is a here? A is divisor. Okay? B is dividend. Okay? So from this theorem, we can say that if we have two integers, a and b, these two integers can be written as this form. Okay? So they will exist q and r such that b equal a times q plus r. So let's prove this theorem. Let's prove this. Let's prove this theorem So we're gonna let A and B be integers, okay, such that A is not 0, such that A is not 0. So what can we do? Since there exists a unique pair, so there will be two parts. The proof of this theorem will has two parts. The first part is to show existence of integers Q and R. That's the first part. The second part is uniqueness of Q and R. There will be two parts for this proof. So let's start with the first part, existence of integers Q and R. Okay, so what can we do with this? Okay, so from this right here, what do I want to show? I got to show that we will show that there exists Q and R, there exists integers Q and R such that B equal to AQ plus R. Okay, where R is greater than or equal to 0, less than absolute value A. Alright, so let's start with cases. Why? Because we have integer A, okay, and A is not 0, and A is an integer. So we will split into many cases. Let's start with the first where A is greater than 0. Okay, A greater than 0. What can we do with this? Okay, so since A is greater than 0, so we know that absolute value of A is equal to A. Okay, and then we want to show that there exists Q and R such that B equal to AQ plus R. So I want to create this set, which is set S, such that it's a set that contains B minus AX. Okay, just like I move AQ to the left side so that we have R equal B minus AQ. Okay, so what is X? X is an integer. Okay, and what next? We're gonna have B minus AX must be greater than or equal to 0. That's what we want to show. So we let S be this set, and we will show that this set is not an empty set. Okay, so what can we do with this? So let's claim that set S is not empty set. Now, let's start with A. We know that A is greater than 0, so this means that A must be greater than or equal to 1, and it is an integer. So what do we have right here? We're gonna have absolute value of BA greater than or equal to absolute value of B times 1 equals absolute value of B. Alright, then what do we have? So we're gonna have B. I try to write the number in this form. So we're gonna have B minus absolute value of B A. Okay, what is minus minus? Minus minus is plus, so we're gonna have b plus absolute value of b times a, and a is greater than or equal to 1, so this one becomes 1, so it turns to be greater than or equal to b plus absolute value of b times 1, which is b plus absolute value of b. Alright, so I try to write the number in this form in set S, like b minus absolute b times a, and it turns out to be greater than or equal to b plus absolute value of b. So what I want to do next is to show that b plus absolute b is greater than 0. And since b is an integer, there will be two cases for b. So we start with b greater than or equal to 0. So what happens when b is greater than or equal to 0? B plus absolute value of b becomes b plus b. So it turns out to be 2b. And since b is greater than or equal to 0, 2b turns to be greater than or equal to 2 times 0, which is 0. So b plus absolute value of b greater than or equal to 0. Now, if b is less than 0, what happened? What happened to b plus absolute value of b? So it's going to be plus minus absolute minus b, which is 0. Okay? Which is 0. So as we can see, what happened? When b is an integer, b plus absolute value of b will be greater than or equal to 0, or it can be b. Okay? So this means that b plus absolute value of b is greater than or equal to 0 for any integer b. Alright? Now, where can we go? Okay. So right now, b plus absolute b is greater than or equal to 0. What happened to this number? So this means that this number which is a number in the form of b minus ax, it turns out to be b plus absolute b a greater than or equal to b plus absolute b, and it's going to be greater than or equal to 0. Therefore, what do we have? So this shows that this term is greater than 0. Okay? Right? So b minus absolute b times a is, what is this? Okay? It's going to be greater than 0. And it satisfies this condition. So once it satisfies this condition and minus absolute b is also an integer, so this means that b minus absolute value of b times a will be contained in set S. That means that set S is not empty set. It's not empty set. So once it's not empty set, what do we have? So there exists, okay, maybe small s in set S such that S is 0, excuse me, or S greater than 0. Okay? Why? Because an element in set S is b minus ax, and b minus ax must be greater than or equal to 0. This means that set S in this set can be greater than 0 or equal to 0. This means that we will split into two cases. The case where S is greater than 0 and equal to 0. Let's start with S equal 0. Okay? Let's start with S equals 0. So what can we do with this? So since small s is in set S, now what happened? So there exists an integer q such that S equal to, okay, let's go back to set S, b minus qx, right? Sorry, b minus aq. Okay, that is b equal to aq plus s when s is 0. Now, because s is in this set S, okay, now we have the existence of q. That's what we want to show. This is existence of q. Existence of q. Okay, so we have q, so that b equal to aq plus s. Now, let's go to another case. The case where s is greater than 0. What happened with this case? What happened in this case? So since s is in set big S, okay, and s is greater than 0, this means that, okay, set S must contain b minus ax, where a and b are integer, x is also integer, but s in this set S is greater than 0. This means that set S is a natural number. So right now we know that when s is greater than 0, set S is a subset of a set of natural number. Okay? Once set S is a subset of a set of natural number and S is not empty set, what can we use? We can use well ordering principle. So the well ordering principle, what does it imply? Okay, so we must have a smallest element in set S, right? So which is R. Suppose that R is the smallest element in set S, it must be less than or equal to all the elements in set S. In this case, which is Y, where Y is greater than or equal to R. Okay? So now, what is R really? R is going to be the minimum element in set S. Okay? Alright, what next? So, since R is the minimum, okay, and S is just an element in set S, right? But R is the smallest. So what happened to S and R? So we're gonna have R, which is S, or S in this set S must be greater than R, right? Because R is the smallest. Okay? So, what can we do next? Okay, what can we do next? Let me think. So now R is in set S. Since R is in set S and R is a minimum, so what do we have? So we will have another Q such that Q prime, which is an integer, okay, such that R equal to B minus AQ prime. Okay, so what happened? We're gonna have B equal to AQ prime plus R. Okay, so we're gonna have B equal to AQ prime plus R. What is R? Where R is greater than 0. Okay, where R is greater than 0. So from both cases, when S is 0, we have this Q and S, right? We have both Q and S, but S is 0. For the second case, when S is greater than 0, we can have R first, and then we have Q, because R is in set S, so that such that R equal to B minus A times Q prime, and we're gonna have B equal to AQ prime plus R, which is the form we want from the existence of Q and R. So from this case, we gonna have, okay, we have shown the existence of Q and R already. So there exists Q and R, integers Q and R, such that, okay, B equal AQ plus R. Okay, B equal AQ plus R. So this one is the existence of Q. Okay, now we already proved the existence, but one thing that we have to show is why R have this inequality. Let's show that R is greater than or equal to 0, less than absolute value A. Okay, let's get started. Okay, so show that R is less than A. Okay, so we're gonna suppose that R greater than or equal to A. So we will show that R is less than A by a proof by a contradiction. So what happened when R is greater than A? This means that R minus A is greater than or equal to 0, right? Okay, and what is R minus A? Okay, what is it? Give me a second. What is R minus A? R is here, right? Okay, so R turns out to be B minus AQ minus A. Alright, then we're gonna have B minus AQ plus 1. And this term is greater than or equal to 0. Okay, and then what next? Since R minus A times 1 equal R minus A, and this number 1 right here is an integer. Okay, and r minus a is greater than 0. Are you familiar with this? R minus a is greater than 0. Go back to set S here. Okay, go back to set S. This one greater than 0. R minus a times 1 is in this term. 1 right here is integer. So this means that QR is in this, R minus a is in this set. Okay? So we're gonna have R minus a, okay, equal R minus a times 1 in set S. Okay? Now, what is R minus a actually? R minus a. R minus a is actually less than R, right? But what is R? R is, where is it? Where is R? Is the minimum in set S. So we have a contradiction because we have an element that is less than R. Okay? R is the minimum. Minimum element in S. Okay? So this is a contradiction. Okay? This is a contradiction. Alright? So therefore, okay, therefore, R is less than A, and A is absolute of, and A is absolute of A. So we've just shown that R is less than absolute value of A. Okay. What about R? Now R is less than A, and R is in set S, right? So R, when R is in set S, what do we have? So we have shown that there exists. What did we show so far? We have Q and R, which are integers, such that B equal AQ plus R, where R is greater than or equal to 0 and less than absolute value of A. Okay, how come can we have R greater than or equal to 0? Because right here R is greater than 0, right? In the case where S greater than 0. And in the case where S equals 0, R is 0. So from these two cases, S is in this position of value, right? R is in here, okay? It's in the position of remainder. So remainder can be 0, remainder can be greater than 0. So this can be conclude that R is greater than or equal to 0. And we've just shown that R is less than absolute value of A. So we're gonna have R less than absolute value of A right here. Okay? Now, what can we do next? This is just the case where A greater than 0. What about the case where A less than 0? Okay, let's do it. Okay? The case where A less than 0. Alright? let's do this. So since a is less than 0, what happened to absolute value of a is going to be negative a. Okay, so from the case where a is greater than 0, what do we have? For the previous case, okay, we know that there exists d and r, right, which are integers, such that b equal to minus a d plus r, which is a times minus d plus r. All right, and then what happened to r? Okay, where r is greater than or equal to 0. Okay, from the previous case, right? And r less than minus a. What is minus a? It's absolute value of a. Okay, so we let q b minus d. What do we have? Hence, there exists q and r, which are integer, such that b equal to aq plus r. Okay, where r is greater than or equal to 0, less than absolute value of a. All right, that's what we have right here. Okay, and this is the proof of the existence of q and r, so that b equal to aq plus r, where r is greater than or equal to 0, less than absolute value of a. Now let's go to the second part here, this one, the uniqueness of q and r. So what do we want to do here? Okay, give me a second. Okay, what we have to do, we're going to show that q and r, which are integer, and show that these are a unique pair of integers, such that b equal aq plus r. Okay, where r is greater than or equal to 0, less than absolute value of a. Okay, that's what we have. Okay, that's what we have. So what can we do this? What can we do if you want to show the existence? To show existence, we can assume that or suppose that there are two kinds of q and two kinds of r, and show that each of these kinds are equal. So we might have first ordered pair, no, first pair of number qr and q prime r prime, okay, which are integer, such that b equal to aq prime, just start with q, okay, plus r, where r is greater than or equal to 0, less than absolute a, and b equal to aq prime plus r prime, where r is greater than or equal to 0, less than absolute value of A. Okay, this is R prime. Okay, then what do we have? It's B, right? These are B. So they are the same. Okay, so we're gonna have AQ plus R equals B, where B is AQ prime plus R prime. So what do we have next? I'm gonna move AQ prime to the same side, right? To the left side. So we're gonna have AQ minus AQ prime equal R prime minus R. Okay? Then it turns out to be A times Q minus Q prime equal R prime minus R. Okay? And then what do we have to do? How to show that Q equal to Q prime, R equal to R prime? Let's use absolute value. Okay? Let's use absolute value. So we have absolute value of A, Q minus Q prime. We know that this inside here is R prime minus R. And R prime minus R is R minus R prime. And then absolute value can be distributed into the product. So it turns out to be absolute A, absolute Q minus Q prime equal R minus R prime. Okay? And then what we need to do next? Okay? So let's try to show this absolute of remainder. I want to show that this remainder is greater than or equal to 0 and less than absolute value of A. Okay, so let's keep it like this and we call it equation A. Okay, and since this inequality, R is greater than or equal to 0, less than absolute value of A, and R is greater than or equal to 0, less than absolute value of A. So what do we have? So we're gonna have, so what do we have? We're gonna have R greater than or equal to 0, less than absolute value of A, and minus absolute value of A, less than minus R prime, less than or equal to 0. Then, what do we have to do? Okay, so let's start with R minus R prime. Okay, and R is, we know that is less than absolute value of A, right? Minus R prime is less than or equal to 0. Okay, so it's less than or equal to A minus 0. Okay, so on the right side it becomes absolute value A. Now what about the left side? Okay, left side. So when for R is going to be greater than or equal to 0, and this one is, okay, let's just write minus R prime, and is going to be greater than 0 minus absolute value A, which is minus absolute value of A. Okay, so what do we have right here? We're gonna have R minus R prime less than absolute value of A. So from this right here, what do we have? Okay, so we're gonna have, okay, sorry. So we're gonna have absolute value of r minus r prime less than absolute value of a, right? And absolute value of a, absolute value of a is absolute value of a. And we know that the absolute value will be greater than or equal to 0 anyway, right? So we've just shown that absolute value of r minus r prime is going to be greater than or equal to 0, less than absolute value of a. So equation A, what does it becomes? Okay, it becomes absolute of A, absolute value of q minus q prime equal r minus r prime, right? Where absolute value of r minus r prime greater than or equal to 0, less than absolute value of a. Now what happened to this equation? Okay, what happened? So we're gonna have absolute value of a, absolute value of q minus q prime equal absolute value of r minus r prime. It turns out to be, because this term equal to absolute value of r minus r prime, and we have this inequality, so it's going to be greater than or equal to 0. Okay, so absolute value of a times absolute value of q minus q prime will be greater than or equal to 0, and it's less than absolute value of a. And divide both sides, divide this inequality by absolute value of a, it turns out to be greater than or equal to 0 and less than 1. This inequality is greater than or equal to 0 and less than 1. Now, what do we know? We know that absolute value of q minus q prime is an integer. So what happened to absolute value of q minus q prime? And this satisfies this inequality is greater than or equal to 0. Q q minus q prime is going to be 0. Okay, once q minus q prime is 0, what happened to r minus r prime? It turns out to be, okay, give me a second. This one is now 0. So it turns out to be absolute of a times 0, which is 0. Okay, therefore, what do we have? Q equal to q prime, right? Okay, because q minus q prime is 0. And r minus r prime is now 0. So we're going to have r equal r prime. So we just shown the uniqueness of q and r. Okay, so we have proved this theorem. So there, so q and r are integer, okay, or unique pair of integers such that b equal to aq plus r. Okay, where r is greater than or equal to 0, less than absolute value of a. All right. Okay, so we have shown the division algorithm already. So if we have two integers a and b, we will have a unique pair of integer q and r such that B equal to AQ plus R, where R is greater than or equal to 0 and less than absolute value of A. Okay, this is a long proof. Okay, that's it for today, and see you in the next video.